Hey everyone, this is Ezekiel O'Callahan with Raptor Chatter, and we're going to be looking at what happened in July 2022 in paleontology. And there's actually quite a bit of really cool stuff, so let's get into it. This first paper is about arguably the most important fossil known from before the Cambrian. And there's been fossils before that have shown at least some indications of some groups that we do know from the Cambrian and even up to the modern day, such as with some potential annelid worm burrows. However, those worm burrows from before the Cambrian still could be interpreted as something that's not actually a worm yet. But this fossil is very definitively from a group that we have in the modern day, and that's because it's a cnidarian. The cnidarians are things like corals, sea anemones, and jellyfish, so a pretty diverse group. But this is again the first fossil that really shows yes, they were here before the Cambrian really started. This new fossil has been named Aurora lumina, and again, the very first known cnidarian, which does line up with genetic evidence that suggests that cnidarians separated from other groups of animals before the Cambrian. So we're starting to find more and more fossils from before the Cambrian that show life was already kicking off pretty well even before the Cambrian actually started. And next we're going to step up into the Cambrian, so just a little bit of time forward from this cnidarian fossil, and look at Unananzoans. Unananzoans may have been the first or among the first chordates, with chordates being things like vertebrates, us, but also some of our closest relatives, such as the tunicates, but also lancelets, which are very small, almost fish-like creatures, but much, much earlier diverging. By using many different types of techniques to look at the chemical structures and some of the finer structures in some Unananzoan fossils, researchers were able to identify parts of the cartilage that were preserved, especially those around the head, which is really important because when we think about vertebrates, one of the most important factors is how the cartilage set up the gill arches. And what the researchers found is that the gill arches in things like the Unananzoans are actually a lot more similar to that in vertebrates than they are in things like lancelets. This means Unananzoans might be really important for understanding the evolution of vertebrates, and especially the jaw of the vertebrates, because we can actually see how that forwardmost gill arch actually follows some of the head shape in the Unananzoans. Meanwhile, in vertebrates, that same cartilage arch eventually turned into the jaw in vertebrates. And as for animals that aren't related to vertebrates but are also from the Cambrian, there was a lot on this, including a new one that was shown to have 3 different eyes, rather than 5 like in things like Opabinia or just 2 like in many Anomalocaris. And it was actually found to be closely related to Anomalocaris, but even more closely related to a separate group that is closely related, the Herdiids. The Herdiids were filter feeders, and the first fossils of Stanleycaris were thought to be very similar to things like Herdia. And that's because it had these more filter feeding type appendages, rather than the large grasping appendages you find in things like Anomalocaris. So it was thought Stanleycaris would have looked a lot like Herdia. But now we've actually looked at some fossils that we've already had and recognized, wait, this is also Stanleycaris, we just didn't know it yet. And those fossils have 3 eyes. What this means is that the single eye in the center may have evolved into the kind of large head shield, not an eye anymore, but just a large head shield, that many of the other Herdiids had. Additionally, it helps to show that potentially having an odd number of eyes is actually just ancestral to the arthropod body plan. And eventually, all of the groups lost an odd number of eyes and evolved an even number of eyes. Additionally, many of these fossils of Stanleycaris also show segmentation, and this is really important when we're thinking about arthropods, because they have a lot of segmentation. You can think of things like shrimp or lobster tails, but even when you look at things like the abdomens of honeypot ants, which expand greatly, you can literally see the segments. And all parts of their bodies are segmented, at least in Stanleycaris, including the head. And the second part of the head actually had a bundle of nerves that would have controlled the arms, meaning that at some point later down the line in many arthropods, there was some compactation to at least some of this segmentation. And still in the Cambrian, quite simply put, bivalved just means 2 shells. And you can think about that most clearly in the bivalves, which are mollusks like clams and oysters, and they very clearly have 2 shells. But there's even some crustaceans with this same type of morphology. In the modern day, these are the ostracods, some of which I've seen even at streams in Arizona, but they're really not that large. And even this new fossil coming from the Cambrian isn't very large, but it's also not a crustacean or a mollusk. It's actually one of the first arthropod relatives. Balhudacaris, caris just means crab, so it's really common in early arthropod names. volte had two large pieces of the shell coming off of its body near the head. And more importantly than that, it actually shows very extreme segmentation, which is funny because when I mentioned Stanleycaris and talked about it being segmented, that was the first time that segmentation was described in one of these early arthropods, at least very clear segmentation. Or at least the authors claimed it was the first time. Meanwhile, this animal also has extreme segmentation. And at least one of the authors on each of these papers is in common, so it's pretty likely they're going to work together about trying to understand when segmentation actually did arise in the fossil record. But it is really exciting to get so many different lines of evidence for very similar things at the same time. Parvibellus atavus is a new animal from the Xinjiang Lagerstätte from the early Cambrian of China. And this animal is found to have a very interesting suite of features, such as a more rounded mouth, like those you find in radiodonts like Anomalocaris, but it's also lacking the large appendages near the front of its head like you would expect in animals like Anomalocaris. Additionally, it has some other features that are more like those of Lobopodens, or at least gilled Lobopodens, which are a strange group of somewhat poorly understood early arthropod relatives that aren't quite exactly like modern Lobopodens, so things like tardigrades and velvet worms, but also aren't quite like things like radiodonts, which are even closer to arthropods. They're really hard to try and nail down exactly what they are. One of these features is that Parvibellus doesn't actually have the same stalked eyes that you see in Anomalocaris, but that the gilled Lobopodens also don't have. That is to say that gilled Lobopodens don't have stalked eyes and Anomalocaris do. So it seems like this new animal is potentially actually the earliest ancestor that we know of both of these groups. And essentially, it diverged off before those two groups diverged from one another, and that could be why it has this strange suite of features that could have led to both of these groups. Essentially, at some point during its evolution, different factors acted on different parts of its anatomy and caused evolution into these two groups that are closely related but still kind of different. So hopefully with more research we'll be able to better understand what was happening with early arthropods. And July was a great month to try and start some of that work. There was also a new Lagerstätte found, and this time not from the Cambrian, but the time just after it during the early Ordovician. And this also comes from China, and the fossils aren't anything totally unique as far as we know just yet. The main things that are mentioned are things like many annelid worms, a lot of trilobites, some bivalves, and some sponges. So again, nothing outrageously unique. These are all things we knew were around, but it does mean that we can actually start trying to get a better idea of what kind of proportions these organisms would have been in relative to one another, and a better understanding of how they would have interacted within the same environment. And next we're moving forward to the Devonian about 350 million years ago, where there were a lot of interesting things happening. One of the most famous of these is Tiktaalik was evolved during this time, and Tiktaalik was one of the first organisms, or at least the first vertebrates, to start moving out of the water. Famously, some people have called it a fishapod, because it's not quite a tetrapod with 4 distinct limbs, but it's also not quite just a fish. It's somewhere in between those two groups. And of course, there's a lot of memes about how people now have to live on land and pay rent and interact with society, and why couldn't Tiktaalik just stay in the water? And the thing is, one of its relatives seemingly did that. It was found to be very closely related to Tiktaalik, but it was also very clearly adapted to live in the water and not on land. This new animal has been called Kikictana wakei and is in a group known as the Opistostegalians. The Opistostegalians were a pretty broad group of organisms that were starting to live more and more on land, and eventually did reach that tetrapod form, or at least most of them other than Kikictania. It is much more partial than the fossils of things like Tiktaalik. However, by looking at its humerus, we can see there's some notable differences. And some of these differences include a ridge that runs along parts of the bone in animals like Tiktaalik, which helps for a lot of the muscle attachment that would have helped them to stay upright when on land. Kikictania just didn't have this, so it's pretty likely that it just didn't go onto land, it just hung out on the water. And this is really interesting because again, it seems like Tiktaalik was already well on its way, and if Kikictania and Tiktaalik are pretty closely related, it seems pretty likely that Kikictania just went, yeah, this land thing isn't my scene, and just went back to the water and ended up staying there. And so then moving into the Permian, and in this case about 260 million years ago, we're going to be looking at some fossils from the Tapnocephalus assemblage zone. And if you want more on what that means, check out my video on Moscops, because I talk about a lot of the geologic setting in that video. It's pretty interesting. But the main thing to know is that there's a main bone layer that contains a lot of Tapnocephalus skeletons. But the thing is, you find other things too. but when they're found alongside those other skeletons, we can define that time period pretty clearly. And that means that these are the earliest known Gorgonopsid fossils coming from South Africa. Gorgonopsids were some of the most dominant predators during the late Permian. And the thing is, the earlier Permian was dominated by things like Sphenacodon and Dimetrodon, which were related but not quite the same thing. They were pelycosaurs. Meanwhile, the Gorgonopsids were closer to mammals, being theraspids. And all mammals are theraspids, but not all theraspids are mammals. So it's one of these kind of offshoots that wasn't directly a mammal, but was still pretty close. And again, they became some of the most dominant predators during the late Permian. And this is the earliest one that we know of coming from South Africa. This new one has been named Phorcys dubyi, and with the rocks that it comes from, it may actually be potentially the oldest Gorgonopsid found anywhere, because most other Gorgonopsid fossils come from parts of Russia, and the two layers of rocks, those in Russia and those in South Africa, haven't been really well correlated. So this could mean this is their first steps in evolution to where they would then go on to dominate the predator niche across the planet up until the end Permian extinction, which is pretty rough for most life. And as I mentioned that extinction, we can actually start pivoting into the recovery from it, because 95% of life in the oceans died and up to 75% of life on land died. So again, it was very, very destructive. But now from the early Triassic, so just a few million years after this extinction, we're already starting to get some diversification coming from some rocks in China at least. Saurosphagiforms were a group of turtle-like reptiles coming from the Triassic, and they seem to have been pretty closely related to things like the Sauropterygians, better known as plesiosaurs. The nice thing about this new one, Pomolyspondylus bni, is that it actually has a lot of very importantly preserved features along the back and the ribs, despite it being overall pretty incomplete except for the back and the ribs. And that does mean we can actually help define what the Saurosphagiforms actually were a little bit better, with a couple of new features. For example, some of these include things like a combination of traits like the presence of dorsal osteoderms, so bones in the skin along the back, as well as the gastralia, so the belly ribs being flattened and elongated, as well as the sidemost elements of the gastralia being broadened and coming into contact with one another, helping to form the kind of shell that we would associate with something that is turtle-like. There's a number of other features mentioned as well, and again, it's a combination of these features, not any single one that can help define them. But despite the fact that Pomolyspondylus was so incomplete, just being those parts of the ribs and the back, it does mean that we have a better understanding now of what some of these early Triassic things were. And the fact that they showed up so quickly in the Triassic just after the extinction really goes to show just how quickly recovery can happen even after some devastating events. The Pachypleurosaurs, like the Saurosphagiforms, also seem to be another group of primarily aquatic reptiles that evolved during the early Triassic, and they actually may be even closer to the Sauropterygians or a part of Sauropterygia, depending on who you talk to. And there's a new one coming from the Swiss Alps. Prosantosaurus schaeffoldii is known from 8 total specimens, and it really does show that there's a lot that still needs to be studied with these organisms, because it has a lot of features that were thought to be totally unique to other animals that were also parts of the same group. Also, I just want to take one moment to just geek out about this figure, because if you look down the middle of it, you can see where they actually separated out the important parts of the animal, but still lined up where the skull, the neck vertebra, and the shoulder girdle would have been, which is just really cool figure design. I really love this figure. It's great. Unfortunately though, again, as great as it is, it still also shows that we need to do a lot more work to try and understand what exactly was happening with the Pachypleurosaurs, so that hopefully we can try and get a better understanding of how we actually eventually reached the Sauropterygians and why things like Pachypleurosaurs, but also things like the Saurosphagiforms went extinct during the later Triassic. And moving on to land in the Triassic, we're going to be looking at Mosasaurus, which was a type of sauropodomorph which lived during the very late Triassic. And researchers actually did bone histology, meaning they cut into the bone, made really thin slices of it, shined light through it, and tried to see what they could find out about its growth rate, and they found a lot of different things. First, that there was either a lot of plasticity, meaning that it could essentially slow its growth rate if there wasn't enough food, or potentially that there was sexual dimorphism, with some of them growing faster and some of them growing slower, based potentially on which sex each of the animals was. And one of the big factors of this is there's a pretty broad range for when these animals likely reached sexual maturity, with it being estimated between 23 years of age and 31 years of age. And that's a pretty significant difference when we're considering the different times that organisms do reach sexual maturity. So either again, there's plasticity where it can vary just based on what resources are available, or maybe there was just a lot of sexual dimorphism in Mosasaurus. This timeline is also a lot more delayed than it is in a lot of other early sauropodomorphs. So things that aren't quite yet sauropods, like Mosasaurus, but also are still towards that lineage towards sauropods. And the thing is, the later sauropods, the Eusauropoda, which are more famous things like Diplodocus, they actually have their sexual maturity onset much closer to things like Mosasaurus. So potentially it could be a sign of everything more closely related to the larger sauropods than Mosasaurus also having this kind of growth rate, or it just means they both evolved that independently. And we're going to stick with dinosaurs, and even in the Triassic, but in a roundabout way, because when we think about Arctic dinosaurs, we think a lot about the fossils that have been found in places like Alaska, but during the Cretaceous, so another 100+ million years later. Meanwhile, what we've actually found is evidence of glaciation in some parts of Triassic rocks coming from China, and this is during the very late Triassic. And the thing is, the dinosaurs, up until that point, weren't doing the best. They were still around, but they definitely weren't nearly as dominant as they became in the Jurassic and Cretaceous. Instead, there were other groups, like the Aedosaurs, which were herbivorous crocodilian relatives, and the Rhyasuchians, which were carnivorous land-dwelling crocodilian relatives. And both of those groups were doing better for the most part, at least during the Triassic. Essentially, they were more common during the Triassic than dinosaurs ever were. But then we get this large faunal shift, and what it seems like is it might have something to do with that glaciation. The researchers suggest that some volcanic activity around the world during this time may have caused at least brief volcanic winters. And the thing is, if you're something that's cold-blooded and you can't survive one volcanic winter, you're gonna go extinct. But if you're something like a dinosaur, which was potentially warm-blooded, there's a good chance that you actually didn't have to deal with those cold temperatures in the same way, and you could actually succeed much better. And this actually makes a lot of sense when we consider other groups that did pretty well, including some of the mammals, which there's another paper on that I will get to in just a little bit that also helps to suggest that. But the important part to realize is just that it's pretty likely that dinosaurs were already very early on warm-blooded, like the pterosaurs were. And that the reason the pterosaurs and the dinosaurs were able to get through the Triassic-Jurassic extinction so well is simply because they were warm-blooded. They didn't need to struggle during these winters as much as other groups did. And this next paper actually plays into the hands of the last ones, because it's about a crocodilomorph, and it's not a complete crocodilomorph, so there's no new name for it. It's just known that it is a crocodilomorph from the very late Triassic, but specifically from areas like Texas, where it was actually at the equator, which if you're something that is cold-blooded and there are very bad volcanic winters, you're probably going to be most successful where it's the warmest. And the equator's pretty dang warm. So it seems like this fossil is actually a really good indicator that, yeah, some of the different pressures that did force the crocodilians and their relatives like the Rhyasuchians to become less successful are actually the same pressures that allowed the dinosaurs to become successful. And on the subject of warm-bloodedness and cold-bloodedness, or endothermy and ectothermy, there's also mammals to think about. And what these researchers were thinking is, how can we tell if an animal is warm-blooded, or at least a mammal relative? And it actually has to do with the inner ear. Because as body temperature increases when an animal starts to become warm-blooded, the fluid in the ear is going to be less viscous, meaning it's going to flow and slosh around more. And the fluid in the inner ear is really important for understanding how organisms can actually balance themselves. Essentially, there's a series of semicircular canals in the ear, and as the fluid moves through those, it essentially gives the organism some sort of sense of positioning in a 3D space. So when you turn your head, and you can feel that your head is turned, that's because the fluid in your ear is moving downhill. And so those semicircular canals play a very important role in understanding how actually movement and positioning works. And if it's sloshing around a lot more, those organisms aren't going to be as good and as precise in moving. But they could just change the shape of those ear canals in order to deal with that new sloshing. And what researchers found is it's pretty likely that all mammals initially were already fully warm-blooded, rather than some of them potentially being semi-warm-blooded or even cold-blooded. Additionally, it suggests that mammals and warm-blooded mammals evolved first during the very late Triassic. Meanwhile, all things that were related to mammals but not quite yet mammals, it seems like they were still all cold-blooded rather than being warm-blooded. And so this is really interesting for understanding how mammals came to become so successful later in the Jurassic Cretaceous, and then especially after the Cretaceous extinction, which led to the broad diversity of mammals that we have today. And moving closer to modern day, even still, we're going to be looking at the Middle Jurassic this time instead of the Triassic. And so this is going to be about 160 million years ago with a new fossil of a salamander. Salamanders are unfortunately very, very hard to study, and that's because they generally don't fossilize well. In general, they have very small fragmentary bones, and many of the ones that we do actually find are preserved in things like sheets. And by that, I mean that some of the ones from places like some of the Chinese Lagerstätte are literally flat. They're just smushed to millimeters thick, if that. This one, though, is well preserved in 3 dimensions. Marmorerpeton is already known from Scotland, but again, this is a new fossil of it, and it's preserved in great 3-dimensional space, meaning we can actually get a better understanding of what this organism would have been like. Additionally, it's more complete than the other specimens. And while it doesn't really lead into a lot of what we need to understand right now, it does mean now we have more fossils to work with than just a handful of Lagerstätte ones that have been completely smashed. So hopefully there will be more work for us to understand better how salamanders evolved into what they were, and potentially even tying them back to other types of amphibians, like potentially the temnospondyls, even further back in their evolution. Because salamanders and even frogs still just kind of show up, and we don't know exactly what group of amphibian-like organisms they actually did evolve from. And next we're moving into the late Jurassic and the Morrison Formation, and into parts of the Cretaceous with the Dinosaur Park Formation to try and understand what the kind of predator-prey dynamics would have been. And this study looked at the number of megaherbivores, so very, very large herbivores, and megatheropods, so very, very large carnivores. And it found that there's actually more carnivores than you would expect relative to the number of large carnivores today and their number of prey. So essentially, when you look at something like the Serengeti, there's a certain number of lions for each prey animal. And what researchers are finding based on the fossil record in the Morrison Formation and Dinosaur Park formations is that there's more predators than you would expect for the number of prey in those formations. So it's kind of a reversal of what we'd expect based on modern day trends. And there's a couple potential reasons for this. The first is pretty simple. Maybe just the carnivores get fossilized more often. Maybe they're living more dangerous lives that cause them to just drown in rivers and get buried more often. There's a lot of different reasons that could be just a preservation bias. Additionally, there's other organisms that would have been hanging around that weren't really used in this study. And these include things like, for the Morrison Formation, Dryosaurus, which is a lot smaller than large animals like Diplodocus. What this means is that things like Allosaurus were probably also eating Dryosaurus, and that just didn't really factor into their calculations quite yet. Additionally, it could just be a mistake with mass estimates. We have what we think are good mass estimates for things like Diplodocus, but also what if we're wrong and it was actually a lot chunkier? If it's chunkier, that's also going to provide more meat for the theropods, meaning that, yeah, those numbers are going to seem off because we're seemingly just getting the wrong amounts for what we think we should be putting in. On the flip side of that, maybe the theropods just needed less food than we actually think they needed. So that would have also compensated for that, because then they wouldn't need to have hunted as often, and one organism like a Diplodocus would have gone a lot further to sustain a population. So there's a lot of variables that are important, and again, this tracks over both the Morrison Formation and the Cretaceous Dinosaur Park Formation, so there really needs to be a lot more study. And the really unfortunate thing about this is, especially with the smaller animals, there's going to be fossil preservation biases against them because they're smaller, they're going to break apart easier, they're going to more likely be hunted, and then they're not going to fossilize. So there could be a lot more potential for that, especially be one of the main reasons that the numbers seem so off to what we would expect based on modern day ecosystems. And as for the end Cretaceous, a lot of things died when the rock hit. I mean, giant fires around the world, it's going to be pretty bad for a lot of life. However, when we actually cored the sediments beneath and above where the actual impact happened, we found a number of different things. For example, first, this Proto-Caribbean Sea where the impact occurred, it was pretty full of life. There's a lot of ichnofossils of different organisms from just above the impact layer, meaning that there were a lot of things like worms, clams, and other organisms crawling through the sand. However, then there's the impact layer, which obviously is a bunch of shocked rock that was just completely destroyed by a giant rock from the sky. It's kind of what you would expect. But pretty quickly after that, as sediment started to fill in the crater, we actually get more and more of those ichnofossils, meaning even relatively close to the impact zone, some of these organisms that were under the ground and in the sediments still did pretty well. and is a great example of how even though one impact can be very devastating for all kinds of life, it doesn't necessarily impact all kinds of life in the same way. One of the groups that couldn't actually bury themselves in the sand were the ammonites, and there was a study to try and understand how ammonites worked, and they did a number of different things, such as using some digital models, but they also made a robot ammonite, which I think is really cool and funny. Ammonites had what's called a siphon, and this is the same structure you can see in squid, where they use it to use a jet of water to propel themselves backwards. And ammonites aren't built quite the same way as squid, so it's unlikely they had quite the same maneuverability, but it does seem like at least some of them had some maneuverability. For example, some of the straight-shelled ammonites probably could move pretty quickly in just one direction where that point was, but still pretty quickly, which is good if you're trying to avoid predators if you can even just go only in one direction and just zoop out of the way of something like a Tylosaurus mouth. But then there's also the rounded ammonites, and it seems like the skinnier, flatter ones were able to jet further on a single pulse than the more wider ones were, which makes sense. However, the wider ones were also able to better control themselves and their positioning in a 3D space like the water, meaning that there were a lot of different strategies that made the ammonites so successful up until the ocean ecosystem was entirely destroyed by a giant rock from space. And a lot of this is actually just laying down the groundwork to do more research on ammonites in the future, but it's still really important to have these steps so we can try and refine some of these experiments. And now for other life strategy things, we can think about birds, because the bird pelvis actually points backwards from their closest relatives, the theropod dinosaurs, because the theropod dinosaurs are part of Saurischia, which is the lizard-hipped dinosaurs, which doesn't make a lot of sense because they're not related to lizards. But it does make sense when you understand how lizard pelvises actually have the pubis pointing forward, and in most theropod dinosaurs, the same thing is happening. And this brings up an interesting question when we're considering how these animals develop, specifically how birds develop from an embryo into an adult bird. And one of the important things to understand is the phrase ontogeny recapitulates phylogeny. And all that means is the development of an organism copies the evolutionary steps that organism took. And that's a huge simplification. There's a lot of debate about how important this actually is, but there's at least some cases where it's true, and it is true in bird pelvises. During some parts of embryonic development, some researchers actually CT scanned the eggs and these embryos, and were able to see, yeah, the pelvis is pointing forward and then pivots backwards later in development. This is something that wasn't really fully understood, and it's still going to be debated how much this kind of principle of ontogeny recapitulates phylogeny actually does matter. And again, it's definitely not a hard, fast rule you should use in every case, but it is a useful tool for helping to understand things, which is why the researchers also looked at the phylogenies of theropods leading up to the birds and found the same sort of morphologic changes that we see in the developing embryo. So again, it's not a hard, fast rule, it's just a tool to help us understand other parts of evolution even better. And staying in birds, we're going to be looking at one that at least some humans actually interacted with, and that's Leptotylops. And in fact, people interact with it today, because this genus is actually a day of modern-day storks, most famously the marabou stork, but also a few others. However, Leptotylops robustus was even larger than these. It's kind of a giant stork, and new fossils of it have helped us understand what its potential lifestyle would have been. And first of all, it doesn't really seem to be the kind of flapping bird, much like the modern marabou stork is, instead using major heat currents, kind of like vultures do as well, to circle up higher in the sky and then gliding for long distances, which made it harder for these organisms to cross large bodies of water. But sea levels were also lower back when this animal lived a few thousand years ago, and that means it could have made it to places like the island of Flores. Flores is actually pretty interesting paleontologically, at least with its recent history, and that's because even these bones of Leptotylops were found alongside bones of other organisms. Some of them were things like Komodo dragons, which don't live there now, but definitely used to. But you also have things like some large vultures, as well as Stegodon, which is an elephant relative, but on this island it became dwarf, but also Homo florensis. Now, Homo florensis is really interesting because it is a species of human, the same way Homo neanderthalis is the Neanderthal, another species of human. Homo florensis, though, is sometimes called the hobbit, because like the mastodons, it also became a dwarf. And so standing about 3 foot tall, this human species was pretty different than what we have today, and even in broader places, like Homo neanderthalis in Europe was pretty similar size to modern day Homo sapiens. This thing just wasn't. And so it's really interesting to understand how the environments in floras may have actually functioned, with Stegodon being potentially one of the major food sources for many organisms on this island, and potentially scavenging being very important, with many of these different scavengers like Komodo dragons, Leptotylops, but also things like the large vultures and even Homo florensis potentially all fighting over carcasses. And sticking with birds in Southeast Asia, we're going to be looking at some pretty recent bird fossils coming from Vietnam. And Vietnam has been really unfortunate in not having a lot of paleontological work done, but it also makes sense when you consider their history of being colonized by the French, colonized by the Japanese, colonized by the French again, invaded by the United States, fighting a war against Cambodia because the Khmer Rouge were killing people, and then being invaded by China. The point is, they've had a last couple of decades. And the thing is, now we're starting to get more publications about what may have been happening paleontologically in parts of Vietnam. Now, this research was actually done in the 80s with a joint expedition with Bulgarians. However, it does mean that we can actually start trying to understand what some of the paleontology was in Vietnam and hopefully know where to go forward from there to try and get more done now that they're not at war with the world trying to invade them. Now, there's a lot of bird fossils that are actually mentioned. And the most interesting thing about them isn't necessarily all of the ones that are named, but essentially that the ones that are named, now their modern day ranges are shifted a few hundred kilometers to the north. And that makes sense because these fossils would have came during the Pleistocene during many of the ice ages that were present in the world at that time. Meaning that if they wanted to live in those somewhat colder temperatures, but not too cold, they would have needed to move south. And then once the ice ages ended and the world started to warm up, they needed to move back north to track those same temperatures. So it's a way we can actually see some of the modern day population shifts towards the north, even today with climate change. Additionally, there's also evidence of some of the humans that made it to this area using some of these birds as food sources, which makes sense. The most common bird found in these deposits, in these caves, is Gallus gallus, the red jungle fowl, or as it's known in its domestic form, the chicken. So even the first people to make it to Vietnam recognized the chicken. Chicken tastes good. And staying with evidence of humans using things as food sources, there's a new mammoth found that shows evidence of humans butchering these mammoths and essentially cutting the meat off the bones. The important thing though is that this is in North America on the Colorado Plateau, or at least the New Mexico part of the Colorado Plateau. And importantly, this falls in line much more with what the indigenous history suggests was the timeline for the first peoples arriving in the Americas. And that's because, in general, the indigenous timelines have been far longer than what the geologic evidence has said, with a recent find of some human footprints that are about 22,000 years old in White Sands, New Mexico, suggesting, oh yeah, look, it is a little bit closer to what they said. These mammoth fossils, though, are from 37,000 years ago, which is much, much more in line with what indigenous histories have said. It's almost like the indigenous peoples of North America know what they're talking about. But again, super important for trying to understand how humans actually did eventually start migrating to North America. And the types of stone tools found at the site, including some things that are just chips of types of chert and flint, are very similar to the same kinds of stone tools that were being used in parts of Eurasia at the same time. Meaning that they are pretty much in line with what we'd expect from the archaeological evidence too of how were humans developing in this location at this time. Now, while this does align with indigenous histories, there is also important to consider that there were probably two groups of migrations to North America. Essentially, both of those created the Native American populations or First Peoples populations that we have today. And so this is really indicative of just the first wave of that migration, and then a second wave of migration would have occurred later on and led to what we have today. And then there were a number of papers I already did separate videos on. The first one was about Tyrannosaurus rex and how we really should just call it Tyrannosaurus rex and there shouldn't be more species. There's a lot of detail I go into in the video for this one, so feel free to check that out. The next one also wasn't that far off from Tyrannosaurs, because it was also on a Tyrannosaur, this one being Eotyrant from the UK. And they were able to actually show a couple of different things about how it was different than the later Tyrannosaurus rex and other large Tyrannosaurs. There's a lot of really cool stuff about this, including some of the stuff with the phylogeny, and especially with Megaraptora being placed as Tyrannosauroids. And the difference between Tyrannosauroids and Tyrannosaurids is something I go into in the video. Check that one out too, because I honestly really like that. It was even tweeted out by the lead author, Darren Niche, because he approved of the video and thought it did a good job. So, proud of that video. Feel free to check that one out. And the last one we did was on Meraxes gigas, which was a large carcharodontisaurid coming from Argentina. And really importantly, it had very well preserved arms for a carcharodontisaurid. And that means we can really understand that the carcharodontisaurids, like the tyrannosaurs, just shrunk their arms to ridiculous proportions. So big head, little arms, seem to be a pretty consistent body plan for a lot of large carnivores. Except for the Megaraptorans, which again, check out my Eotyrannus video for that one. But if you want to know more about the shrinking of arms in carcharodontisaurids, check out my Meraxes video. Hey everyone, thanks for watching. Be sure to check out our Patreon where you can try and help support us for doing more videos. Feel free to check out the Discord where you can see people share papers, memes, and discussion about paleontology topics. It's really cool seeing some of these papers, like especially I'm not that into human evolution and migration and archaeology, but the one with the mammoths showing that, yeah, no, the first indigenous peoples in the Americas made it here much earlier than other evidence has said, is really cool for being like, huh, it's like they were right. With all that being said, everyone keep in mind to be safe, take care, and don't go extinct.